In this video, we're going to talk about periodicity. We'll cover the different types of structure that you have as you go across the periods, and we're going to talk about specifically the structure and the melting point and go through versions of giant metallic lattices, giant covalent lattices, and simple molecular lattices, referring to different types of forces. First of all, simple molecular lattices. They are simple molecules which have a definitive number of atoms with a definitive molecular formula. And so you're used to this kind of formula for lots of different molecules that you use on a regular basis. Now, the atoms are held together by strong covalent bonds. And the molecules, though, are held by weak intermolecular forces such as hydrogen bonding, permanent dipole-dipole, and London dispersion forces or London forces, which are also called induced dipole-dipole forces. They all have low melting points and boiling points because there's not a lot of energy needed to break those different types of intermolecular forces. And they don't conduct electricity because they have no free electrons. For electricity to flow, you need free electrons or you need mobile ions. We're now going to go on to giant metallic lattices and talk about a common exam question. So first of all, you need to know the definition, which is metallic bonding. Now, the metallic bonding definition is the strong electrostatic attraction between positively charged ions and delocalized electrons. As long as you mention the positively charged ions and the delocalized electrons, you'll be fine. Sometimes you can say positively charged metal ions, and that's still correct. Now, how does this happen? This happens because you have, in our example, Mg, which is going to Mg2+. Now, as it goes to Mg2+, it loses 2 electrons. Now, the 2 electrons it's lost are the delocalized electrons. So if we're drawing a diagram, let's draw our atoms that we're going to turn into ions. And we can see there's only 6. So I would recommend, if you're ever going to do this, just do 6. You don't need to do any more. They must be regularly arranged in a line, 2 lines like that. And it's really important that they're regular so they look like a lattice. Then for each atom, we can draw the number of electrons it loses. So for magnesium, it loses 2. And so we're putting 2 in for every single magnesium. Those red dots have now really turned into magnesium ions. But at the moment, this is a picture. This is not a diagram, it's a picture. So if we look here and we say, right, how can I turn it into a diagram? Well, you do that through labels. So make sure that you have labels on any diagrams you do in any of your chemistry A-level. Now we've got 2 labels. The label is just the same as the definition really. So we've got to do positively charged ions, and as here we've been more specific and said magnesium ions, which are 2+, and we've shown the delocalized electrons as well. Doesn't matter where the delocalized electrons are, they can be random all the way through. So let's look at what properties this actually gives. So one of the properties it gives is conductivity. So if you look at it simply, on the left-hand side of the periodic table, you've got the metals. Now, they all form positive ions. That means they're giving out electrons. They're giving out electrons that become delocalized. So that means those delocalized electrons cause the metals to be good conductors of electricity and heat. That means they can flow through the metallic structure and carry current. Now, if you look at the opposite, you can see non-metals. They form negative ions, which means they take in electrons, which means those electrons aren't free to flow. They're not free, which means they don't generally conduct electricity very well. If we summarize this, we can look at all the properties of metals. First of all, that high conductivity we've mentioned. Okay, that's because of the delocalized electrons that can move through the structure and carry charge. It's very worth remembering that sentence. That will get you marks. Okay, now, high melting point and boiling points, essentially, are due to the fact that you need a large amount of energy to break that electrostatic attraction between the cations and the delocalized electrons, that strong metallic bond. So refer to the strong metallic bond that takes a lot of energy to break if you want to explain high melting points and boiling points. Now, the question we want to go through is how to explain those melting point differences in more detail. So we have 2 metals here, lithium and beryllium. We can see beryllium has a much higher melting point than lithium. And the question is asking you to explain the difference using a model of metallic bonding. If we put this over to the right, okay, And then we look and we see we've highlighted that higher melting point, which is much higher than 180, about 1,000 degrees higher, and we've highlighted the model of metallic bonding that we need to use to answer the question. So if we bring up our model, which we did before, this time we're going to do lithium. So lithium loses one electron, and therefore let's put one of our electrons on each one. Okay, and this is a picture, not a diagram, so this is not mark-worthy, so let's make it into a diagram. We've got our lithium ions, Li+, and we've got our delocalized electrons. Let's compare this to beryllium. So beryllium, again, 6. And we've got 6 here. So how many electrons are we losing per beryllium? We're losing 2. It's in group 2, so it loses 2 electrons. So let's put those 2 electrons on. So we've got 2 electrons, and you can see immediately the difference between these two. Lots more delocalized electrons here, fewer delocalized electrons here. So that's important to note down for answering this question and explaining the melting point. First marking point. But let's finish off our diagram, put our labels on. Let's also look at the other difference. The other difference is I've got a 2+ ion here. I've got a lithium plus ion here. Okay? And what that does is 2 things. One, it takes the ion and it makes the ionic radius get smaller. If you think about it, the protons attract the electrons. So the protons are in the nucleus and they attract the electrons which go around. The protons are positive, and if you have more protons than you have electrons, they're going to pull in those electrons a tiny, tiny bit. So that makes the ionic radius just a tiny bit smaller. Now that means the increased charge that we have, the Be2+ has 2+ charge, this has a 1+ charge, the increased charge we have is spread over a smaller area. And that's referred to as a higher charge density. We're going to show that in a tiny way when we rearrange these diagrams. So when I rearrange these diagrams, you can see that the ion's got a tiny bit smaller. You can just see it's just a little bit smaller here. And so that is a smaller ionic radius, and it has more outer delocalized electrons, so it's a higher charge density. So its higher charge is spread over a smaller area. Now that means that it has a greater attraction between the ions and the delocalized electrons, a stronger metallic bond essentially. But it's really important that you mention these delocalized electrons, the charge density, and this greater attraction, and that will get you marks in this question. Now let's start talking about giant covalent lattices. So we've started with diamond. So diamond is made of carbon. So there are 4 atoms of carbon around a central atom of carbon here, and you can see that this is carbon because it has 4 electrons in the outer shell. So 4 electrons in the outer shell. We haven't drawn the inner shell. 4 electrons in the outer shell. This is carbon. So we've got bonding between these 4 carbon atoms and this central carbon atom. The diamond, being made of carbon only, is a giant lattice that continues forever, like this. Now you can see though, there are a bonding pair of electrons there, 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 and there. So there's 4 bonding pairs of electrons for each carbon. Right? And this can be illustrated in a diagram. So if we look here, we can look at this one right here. Let's look at this carbon and look, well there we have 1, 2, and we got 3, 4. So we've got 4 atoms connected, and you can see the bonds there. Okay, so that's 4 atoms connected to the central carbon, just like we have in our diagram over here. Okay, but this time this is just showing a small cell of the whole thing instead of just 1 carbon connected to 4. And you can see that we've got these pyramids in here, and that's showing the faces. So what there are 4 faces around each carbon. And face is also referred to as hede, and 4 is tetra. So if you've done your bond angles learning, you'll know that 4 bonding pairs is going to be tetrahedral. Tetrahedral means 4 faces. So if we draw this, there's 4 faces around the central carbon. Now if we put that to the side, okay, and then we go over that again, we have 4 strong covalent bonds because of 4 bonding pairs of electrons. 4 bonding pairs of electrons is tetrahedral, 109.5 bond angle. So 4 faces and a 109.5 bond angle for tetrahedral. So that's how diamond's structure is. Now, as a high melting point, due to the strong covalent bonds that we've got here, all covalent bonds are very, very strong, okay? And they require a large amount of energy to break. It is insoluble due to those strong covalent bonds, which again take too much energy to break, so water can't break those bonds, so therefore it's insoluble. It does not conduct electricity as it has no free electrons. Notice in our diagram that all the electrons are bonded up in this one. Remember, we haven't drawn all the ones around the outside. So here you can see they're all bonded. And in this diagram here, you can see they're all bonded. Okay, there's nothing free to move. So it does not conduct electricity. Our next one is graphite. So graphite, we're going to show just the carbons here again. This time you notice there are 3 carbons around the central carbon. Now let's put the electrons from the central carbon in, and you can see that there are 3 from the central carbon, and you see 3 from the other carbons, but you can notice a subtle difference. There are 4 electrons on the outer carbon, so 4 electrons, but there's only 3 on the centre. It's because it does have 4, as we're showing here, but that 4th one is delocalized, which means it can move away from its atom. So let's move it away from the atom. Now that is delocalized. Now, if we talk about the structure of graphite first, before we go on to talk about what that delocalized electron actually means. So first of all, graphite has 3 strong covalent bonds, and you can see the 3 bonding pairs over there. Now this means that it is a trigonal planar bond angle. Trigonal planar requires 3 bonding electron pairs, or 3 bonding regions of electrons. Now this has 3 bonding pairs of electrons, and therefore it's trigonal planar 120 degrees. If we look at the structure a little bit more closely using a model, and you can see here, just like I've done up here, you can see this carbon surrounded by 3 others. Okay? Now, that means that because it has these 3 strong covalent bonds, it also has a high melting point due to those strong covalent bonds that require a large amount of energy to break, just like we had in diamond. And it's really important you say large amount of energy to break. It also has the same property in that it is insoluble due to the strong covalent bonds, which take too much energy to break. Now let's look at another property. So let's take that delocalized electron and put it in between the layers. Now in graphite, you have these layers, which I showed you in the previous slide, but here we've got the layers sitting on top of each other. So this is individual layers of graphite. Now those individual layers are called graphene, but when they're together with all these layers, they're called graphite. And you can see that there's 1 delocalized electron per carbon that is in the center here. Now that delocalized electron is free to flow. Now if it's free to flow, you might think, well, what property does that give? Well, if it's free to flow, that means it can conduct electricity. Now diamond can't, graphite can. Okay, so it can conduct electricity, so it has different uses. Also, the delocalized electron gives a London dispersion force between the layers. Now that London dispersion force is really, really weak, which means that the layers slide over each other. Okay, so because of those, it can be used in pencils and as a lubricant, but we'll talk about that later. So there's our layers, there's our delocalized electrons, and let's summarize again. So graphite does conduct electricity, as it has delocalized electrons which are free to move through the structure and carry charge. Again, very good for you to remember that sentence. Through the structure, carry the charge. It can be used as a lubricant and in pencils. Now that is because the layers, as we can see on the right, can slide over each other as the weak London dispersion forces break between the layers. Now we talked briefly in the last slide about graphene. So 1 layer of graphite is referred to as graphene, and we can now, with the wonder of science, separate out those layers and just get 1 layer of graphene. Now it has the same properties as graphite. So 3 strong covalent bonds, because of 3 bonding pairs of electrons, trigonal planar, 120 degrees again. It has the same high melting point, strong covalent bonds that take a large amount of energy to break. And it still conducts electricity because it has delocalized electrons which are free to move through the structure and carry charge. But it has other uses other than graphite. So let's look at a couple of those. So one use is graphene nanotubes. And you can see in this handy graphic here, we've got a rolled up tube. Okay. Now that means that tube can conduct electricity. That means that tube is light. It's a low density, but it's very, very strong because it's got strong covalent bonds. We just summarize that and give a couple of uses. Okay, it can be used as fibers in polymers. Improves the mechanical because it's strong, the thermal and electrical because it can conduct electricity through those delocalized electrons. It can be used in bike parts, and that's because it's rigid, strong and light because of these strong covalent bonds. Now, another example of a giant covalent lattice is silicon. Now, silicon has an extremely high melting point. So you may not be surprised by this point because all giant covalent substances have strong covalent bonds. So let's look at a model. So the model here, you can see our central silicon here surrounded by 4 silicons around the outside. So we've got one there and then we've got one down there. Okay. So 4 silicons. If we zoom in on that, it's a bit easier to see. And you can see the 4 we've got here, 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 and the one down here. Okay, so again, I'm hoping you can see at this point and you're saying, well, that must mean the bond angle is tetrahedral, okay, 109.5. So 4 strong covalent bonds, 4 bonding pairs of electrons, tetrahedral, 109.5. Again, you probably predicted this. It's got 4 strong covalent bonds, so therefore a high melting point due to that and the amount of energy it requires to break. The last one about giant covalent lattices is just a question to compare some of these and to see whether you can remember as we're going along. So if you're watching this, try and remember the answers to the questions as I pose them. So let's put graphite and diamond up. And let's first of all look at the number of covalent bonds. So in graphite, it has 3 strong covalent bonds. And therefore in diamond, it would have 4 strong covalent bonds. Clear difference, 3 and 4. Next thing is, what's the bond angle? Well, the bond angle here, if you've got 3 bonding pairs, would be 120 degrees. If you've got 4 bonding pairs, it would be 109.5. This one has weak London dispersion force between the layers. So graphite has that weak London dispersion force between the layers. Diamond doesn't have any London dispersion forces between the layers. It doesn't have layers. This one has a high melting point, and so does diamond. So both graphite and diamond have a high melting point. And lastly, let's look at the conductance of electricity. So if I look at graphite, it conducts electricity. If I look at diamond, it does not conduct electricity. No free electrons, delocalized electrons. And that is a summary of giant covalent lattices, and specifically graphite and diamond. So we've just considered giant metallic lattices and giant covalent lattices and gone through examples as we go along. But now we're going to talk about the trend in melting and boiling points across the period. Now we're going to focus mainly on melting because we don't really consider boiling points of metals and giant covalent lattices. Okay, so most of the time you'll get a question on the melting point, not the boiling point. So let's have a look. What do we have to consider? We have to look at attractive forces that need to be overcome in each stage. So if we're melting, that's, for example, solid to a liquid. And we need to look at the strength of those forces. So what type of force is there? Is it a metallic bond? Is it a covalent bond? Is it, when it comes to it, a London force? We then have to look at the different type here, and then we'll know the forces because of it. So if there's metallic bonding, that's a giant metallic lattice, and if it's covalent bonding, it could either be a giant covalent lattice or it could be a simple molecular lattice. If you look at period 2 and period 3, so we have period 2 here and we have period 3 here. So if you go across, all the ones in grey are the giant metallic lattices. We've got lithium, beryllium, sodium magnesium and aluminium. And then move on to the giant covalent lattice, and that has boron, carbon and silicon. And you notice here the difference. We're going from strong metallic bonds between cations and electrons to strong covalent bonds between atoms here, okay? But both strong, but one being covalent and one being metallic. As we go across the period now, we're going to go to simple molecular lattices. Now, this word molecular, all of these are molecules, N2O2F2, P4S8Cl2. They're all molecules because they're bonded to each other. They're covalently bonded to each other. N is bonded to N, P is bonded to P, and so on. Okay, so these are, and they have weak London dispersion forces between those molecules. And when it comes to neon and argon, slight distinction, if they have, and when we're discussing, their melting point or their boiling point, you need to refer to the weak London dispersion forces between the atoms because they're just atoms. There's no molecules there. They're still, though, referred, and this is a strange definition thing, is that they are still referred to as simple molecular lattices. So let's consider the actual range in terms of the melting point. So we've got the period 3 elements here, and we've got sodium to magnesium to aluminium to silicon, and then we go down. And we've colour-coded these in the same way we colour-coded the table. So basically you've got the metals, you've got the giant covalent lattice, and then you've got the simple molecules over here. To make that a little bit clearer, here are giant structures, and here are simple molecular lattice structures. Now if we look at this, and we then just go in a bit more detail, and we know, for example, that the sodium to the magnesium, we know that the number of delocalized electrons going up, the charge density is going up because the ionic radius is getting lower, okay? And that is why you can see this trend upwards from sodium, magnesium, aluminium. And it's because of strong metallic bonds. If we then go to here, we go to silicon, massive jump up. Again, all we have to say is that's because of strong covalent bonds that take a lot of energy to break. So if you're going to describe this, you want your definition here of metallic bonding. You want to talk about the delocalized electrons, the size of the ion going down, and you want to say there's a higher charge density, and therefore the whole thing is increasing the attraction between the ions and the delocalized electrons, and here just strong covalent bonds. If we focus, though, on the simple molecular lattices, because we haven't talked about those yet. And as we go in here, we can see there's phosphorus, sulfur, chlorine and argon. And I stress to you, you have to, unfortunately, remember the structure of each one of these. So that means that the first structure for phosphorus, you need to remember that it's P4. So we've got P4. Each phosphorus has 15 electrons. That means if you times 15 by 4, you'll have 60 overall electrons in that molecule. If we then do the same thing, and you go S8, have to remember S8, unfortunately. Okay, so it's really important you remember S8. Each one has 16 electrons, times that by 8, you get 128 electrons. So we can see the number of electrons has gone up from phosphorus to sulfur. That explains that the London forces are going to get stronger. The more electrons you have, the stronger the London force is. That means the stronger the attraction between the molecules, and therefore that's why your melting point goes up. Then go to chlorine. Now think about this before I put on. What is chlorine? What's the formula of the molecule? Well, the formula of the molecule is Cl2. In each chlorine, there is 17 electrons. There's 2 atoms, so 17 times 2 is 34 electrons. 34 is less than 60. 34 is much less than 128. So it makes sense that the London forces are weaker, and therefore this melting point's gone way down. If we follow that rule and we go to argon, argon is just an atom, has 18 electrons. That's lower than all of them, which means it has a significantly lower melting point. So when you're describing this, you need to refer to the number of electrons, and you need to remember, really importantly, it is P4, S8, Cl2, and argon. You need to remember those formulas in order to understand this question. Remember, it's all about numbers of electrons. Stronger the higher the number of electrons, the stronger the London force, and therefore the higher the melting point. So let's do this in a summary. So it's really important that at the end of this, what kind of questions are you going to get asked? Well, the question you might get asked is to summarise and explain the trend in melting points of period 3 or period 2, okay, using structure and bonding. And they'll say using structure and bonding. It's quite a long question, so I'm going to stay here and just go down each point in turn. So if we go across, we know we had a giant metallic lattice, sodium, magnesium, aluminium. We knew it was metallic bonding. So there's electrostatic attraction of positively charged metal ion and delocalized electrons. Okay. We know that the charge density increases from sodium to aluminium. That ion gets smaller. The number of delocalized electrons increases. Okay. Therefore, the attraction between the two goes up. And this results in stronger metallic bonds, which take a lot of energy to break. The giant covalent lattice is silicon. Now, silicon is covalent bonding, so I've given the covalent bonding definition here. Attraction between positive nuclei and a shared pair of electrons. Okay, and we also have strong covalent bonds that take a lot of energy to break. We then move on to the simple molecular lattices, phosphorus, sulfur, chlorine, and argon. Okay, and they have induced dipole-dipole interactions, also known as London forces, and they're between those molecules which don't take a lot of energy to break, so their melting point goes down. So if we look at the comparison of strength, we've labelled all the types of bonding or forces. We've labelled those, so we've got most of our marks. Then we compare the strength in period 3. So we're going to compare the strength. Now the strength is quite high when it comes to metallic bonds. You can see the metallic and covalent bonds much stronger than the London dispersion forces. You don't need to go into huge detail on that. You just need to compare the London forces to the covalent and metallic. Okay, and we can see that they're much stronger because the graph went up and then went down. Now this is the point where, if you remember, we had P4, S8 and Cl2 and AR. Okay, and because we had those, we can say that the London dispersion forces are greatest with the larger molecules which have more electrons. And I haven't included all of them, but you can see here that you have S8 has more than P4, for example. But as long as you say the larger molecules which have more electrons have stronger London dispersion forces, then you are fine. So let's do this in a summary, because exam questions here can be talking about how you actually summarise the melting points across a period. Now you can do period 2 or you can do period 3. We've chosen period 3 because we've gone through period 3, but it's very similar in period 2, and I'd encourage you to practice with period 2 as well as part of your revision. So let's talk about the first part. As we went across, remember the graph at the start. We had sodium, magnesium, aluminium, and we know that that's a giant metallic lattice, and therefore we give our definition of metallic bonding. Now that is a positively charged metal ion and delocalized electrons, or you can just say positively charged ion, it doesn't really matter. Okay, and delocalized electrons. We know the charge density increases from sodium to aluminium. Okay, that's because the ionic radius gets smaller. Okay, and the number of electrons, delocalized electrons, increases. That results in a stronger metallic bond, which takes a lot of energy to break, and hence you have those higher melting points and boiling points as you go from sodium to aluminium, and generally a higher melting point anyway than other substances. Now, giant covalent lattice in period 3 is silicon. Silicon has covalent bonding, so I've given my covalent bonding, electrostatic attraction between positive nuclei and shared pair of electrons. Okay, and that's because of strong covalent bonds that take a lot of energy to break. Now, that's all I really need for that. So simple molecular lattice, where it gets a little bit more complicated, of course they are simple molecules, so they have covalent bonds inside their molecules, but between their molecules they have induced dipole-dipole interactions, London forces. So between the molecules, they're weak overall compared to these bonds. Bonding is strong, forces tends to be weaker, and that means it doesn't take a lot of energy to break those weak forces. Now you then, in a kind of question like this, have to compare those strengths. Now, in terms of the metallic bonding and the silicon, you don't have to do much comparison because they're both known as strong bonds. I know the trend goes up, but they don't really require you to do anything more than that. The really important thing is to do with a simple molecular lattice and remembering those molecules, for example P4S8Cl2Ar, that are in the previous slide. So if we look at it, we know the metallic bonds and the covalent bonds are stronger than London dispersion forces, so we've made a comparison. We also know that the London dispersion forces are greatest with larger molecules as they have more electrons, and I've just talked about, for example, P4S8Cl2 and Ar. Now if we know that the larger molecules have more electrons, all we have to say is the stronger the force, the higher the melting point for all. So if I've got a stronger force because I have more electrons, that means the higher the melting point. So I'm finally linking my melting point to my forces and therefore to my number of electrons in the previous line. Now that is the most common question that you can get in exams, but they can also split it up like we did earlier in the video. So for just talking about metallic, just talking about covalent, and just talking about simple molecular lattices.